Okay, we're very happy to have you here, Jay. Jay is from professor at Portland State University. Many of you already know him. I know him from my PhD years. He's an expert in eye of the finite elements, HDG, DPG, stereo calculus, apparently, multigrid methods, many areas. So we're very happy to have you here. Please take it away.
All right. Thank you very much. It's a great pleasure to be here. It's such a storied place, providing leadership in computing for the nation, and with a lot of friends. Good. Thank you for inviting me. I'm going to talk about some developments in matrix-valued finite elements or finite element functions that are matrix fields. This is in collaboration with a lot of people, some of whom have joined and are in the audience. And I'll point out along the way the specific references. Okay, so the plan for the talk is to begin from sort of a familiar place for many of us, which is the lowest order finite elements on a tetrahedra. This is a picture from the now famous poster of Arnold and Bloch called the periodic table of finite elements. You see the Lagrange finite element right here, the lowest order Lagrange finite element that it goes back to the 40s, followed by the Nedelec finite element, which came many years later, 1980, which produced vector fields that have their tangential components continuous. And there is a companion space by the Rabiar and Thomas called the Rabiar-Thomas finite element space, where the natural operator is the divergence operator, and the interface continuity conditions are the continuity of the normal component. Whereas in the previous one, it was the tangential component, which I'm going to refer to as T continuity, and the natural operator was co. And of course, there is the discontinuous Galerkin finite element space, which I don't put a date there because it seems like it's a space of piecewise constants, which has been around since the beginning of time. So, although these spaces have been developed independently, as you can see from the references I just gave, we now understand them collectively in the context of the Rham complex, which connects these spaces using these first-order differential operators: the gradient, the curl, divergence, all manifestations of the single exterior derivative. So one of the interesting frontier questions is, where do we put matrix-valued finite elements into this picture? And by the end of the talk, I'll give you some frameworks in which these matrix-valued finite elements might potentially fit. And they, instead of the first-order differential operators, you'll see that they're connected by certain fundamental second-order differential operators. And I'll begin the discussion by one example. Each of the examples of matrix finite elements is very rich, and there's a whole talk you can give for each of them. But I'll just focus in the next few slides on a second-order operator that is a composition of co and divergence on matrix fields. So the divergence is applied on a matrix field row-wise, and it turns out that NT continuous matrix elements are appropriate for this, and what exactly this means, and it'll be clear as we go. So the application comes from this co-div operator comes from Stokes system, although as you can see from the Stokes system, you don't see the co-div operator emerging from the statement of the equations. So here is the first box consists of the textbook version of the Stokes system, where the kinematic viscosity, when usually it's a constant, and it's taken out of the Laplace operator. In the other box, you see the physical version, which has the conservation of momentum equation, where you see a viscous stress variable, sigma, entering into the first equation. The first equation is essentially the definition of the viscous stress variable, where epsilon is a symmetrized gradient. Although you don't see the Kolev operator appearing here in this form, the question whose answer will lead to that is the question that's written there. What sort of formulation for a well-posed formulation will generate a sigma space that pairs well with an H-div space on U? Usually because the Stokes system is often started from this textbook version, we think of the velocity variable not an H-div, but as something that can sustain the Laplacian, for example, an H1 vector field. But if you change the point of view and we ask for a vector field in H-div, where you only need the divergence, then the corresponding space in which sigma should be paired is a natural space where normal tangential continuity is important. This would be the message of the next few slides as we go along. But first, I want to introduce this mass-conserving stress-yielding method, which is based on the formulation from the second box, where sigma is set as an independent variable. Now, the starting point that I mentioned was placing the velocity variable in fluid flow in H-div. The reason why one would want to do that is to get easily obtain mass-conserving methods. And these videos are trying to show you the importance of mass conservation. So I'm coming at the Stokes flow from the point of view of imposition of mass conservation as an essential feature. This is a Kelvin-Helmholtz instability simulation on a unit square on a 256 grid. The left and right boundaries are periodically identified with periodic boundary conditions, and the top and the bottom, a wind shear is being modeled by opposing boundary conditions on the top and bottom edges. As you can see, the simulation starts with a lot of tiny vortices, and the vortices start pairing up, as you see here, and they keep repeatedly pairing up. So many of the simulations agree on this qualitative behavior. This is what happens when you when you plot a picture of the vorticity from the simulation. But quantitatively, the timing of the pairing is often different simulations. And usually mass-conserving schemes do better. Or we don't know the exact solution here, so we think that the mass-conserving schemes do better. Here is a comparison of the same simulation across multiple different polynomial degrees and multiple different methods. They're all methods of the same flavor. They're all HDG type methods. The first row is an exactly mass-conserving method. K refers to the polynomial degree. The second row is a non-mass-conserving method, which can be post-processed at each step to get a mass-conserving solution. And the last step is an HDG method that is not mass-conserving. It does not produce a Stokes velocity that's exactly mass-conserving. And you can see in a Navier-Stokes, this is a result of a Navier-Stokes simulation with IMAX time stepping, where you're doing a Stokes solve at each time step. You can see that the simulation has blown up and had to be stopped at the bottom row, whereas the simulations continued farther in time in the first two cases where you have mass conservation, exact mass conservation. And when the polynomial degree is sufficiently high, you can see the fine features of the vorticity being captured. So mass conservation is, from the engineering standpoint, It's a condition on the material derivative of the mass density, material derivative of mass density. The incompressibility constraint of a fluid translates into the material derivative of the density being zero. If you look at the mass conservation equation written in terms of the material derivative, this is the mass conservation equation. So you immediately see that in an incompressible fluid, once this is zero, mass conservation is the same as, is equivalent to divergence being zero. So from now on, we'll focus on the divergence-free velocity being equivalent to mass conservation. For a piecewise polynomial fluid velocity approximation, if you want exact mass conservation, you want this divergence of UH to be zero in the sense of distributions, which means it needs to be zero pointwise within each element, and also you need to have the normal continuity, normal component of the velocity to be continuous across element interfaces. Okay, so the discrete version of the incompressibility constraint in any space which minimally has this n continuity or the normal continuity would be an approximation of the equation divergence of u equals zero, and typically it takes this form: divergence of the discrete velocity integrated against anything in the pressure space is zero. So almost all finite elements have some version of this for Stokes' law. So you immediately see that the UH is exactly mass conserving if the divergence of the velocity space is contained inside the pressure space. This allows you to now categorize the methods into two categories. You could think of velocity spaces with full continuity or with just normal continuity. Just the normal continuity falls into this HDiv-based methods. HDiv is, of course, a space where you have velocity components in L2 and the divergence in L2. H1-based methods, this is the notation for vector H1. Every component has a derivative in L2. Here are the trade-offs. If you use an HDiv-based method, then the range of the divergence operator is very simple. It's right, you can see it right from the Rham complex. You know exactly what the divergence is. Divergence lands into and the range of the divergence. What becomes complicated is you have a viscous term with a Laplacian and you have to discretize it. In the H1-based scenario, the range of the divergence is very complex. And this is the message from the papers, the old classical papers of Scott and Vogelius. But the viscous term is easily discretized. It's just a Laplace-like operator. And there are streams of methods and papers in each category. And since I want to get into this matrix valued finite elements, I'm gonna focus on this category, and the mass conserving stress-yielding method falls into the HDiv-based method category. So here are the punchlines of the MCS method. Before I give you the method, the numerical solutions are exactly mass conserving because we're going to put them in HDiv and we're going to enforce the divergence-free condition exactly. The scheme has structure preservation properties, not just mass conservation, but also pressure robustness. And we'll develop a stress approximation which has the property that it's the jump of the normal tangential component, or this thing, is zero across the interfaces. This is the matrix value finite element. And it's optimally convergent in 4 variables: the velocity variable, pressure variable, the viscous stress variable, and the vorticity variable. The method has no stabilization parameters, and what is interesting from an engineering standpoint is right in the formulation, it's easy to impose fluid stress boundary conditions because the stress is appearing as one of the variables. So you could have either essential or Neumann boundary conditions on stress. There are no vertex unknowns, as you'll see, and therefore you can hybridize and condense out interior variables. And there are natural mappings that make even curvilinear elements suitable. And you can go from the gradient to the symmetrized gradient type formulation. These are the punchlines, but now I will try to give you a sense of how the method is derived. So on one side is the standard form for reference, but I'll start with the physical stress-based formulation on the right-hand side. First, we're going to take the first equation and apply the deviatoric operator. The deviatoric operator is defined below. And when we take the deviatoric operator, I'm not putting the deviatoric here because the trace of this is the divergence. The trace of the symmetrized gradient is the divergence of velocity, which is 0 by this equation. So the deviatoric operator falls only there. The next step is to write the symmetrized gradient as the gradient minus the skew-symmetric part. The skew-symmetric part is the vorticity, at least in a skew-symmetric matrix form. So now you see the emergence of vorticity and the symmetry of the stress tensor being imposed as an additional equation. So you see the different matrix fields that arise here. You see that this sigma now should be in the range of the deviatoric. It's a traceless matrix. And omega is a skew-symmetric matrix. Multiplying by test functions and integrating by parts as usual, we'll get a variation formulation, and you have 4 fields and 4 equations. This is the entire equation, the set of equations of the method. This deviatoric operator is a projection, so I could throw that over into the test function, and the gradient has been integrated by part, and that has become the divergence. And the derivation of the method is essentially complete, except for one more modification, the blue terms. We're going to replace the blue terms by functional actions to investigate the minimal possible regularity under which you can make sense out of this type of formulation. Okay, so what does that mean? I've copied over the equations here, and the angular brackets now is the functional action. Now, without going into details of the full theory, we can immediately see that if you want all the terms in this formulation to be continuous in a mathematical sense, bounded in a mathematical sense, the minimal requirement is that this should make sense, or that terms like this, where you have a divergence of this matrix field, this should be able to act on the velocity space in a continuous manner. And we've already fixated on having the velocity space in this H0 div. So therefore, we must have divergence of sigma in the dual space of H0 div. Okay, the dual space of H0 div is equal to a H-1 curl, which H-1 curl is defined below. It's a H-1 vector field whose curl is in H-1. This is one of the many identities that we'll see. We'll return to this at the end of the talk. There are many more identities, duality identities that are analogous to this. Knowing this, we can write this condition as a condition that this being in the dual of H div is the same as saying that the curl of the divergence should be in H-1. Or in other words, the stress space must have this condition. This is how the curl div operator emerges from the Stokes formulation, although it doesn't actually appear in the original system of equations. So whatever is this matrix field for the viscous fluid stresses, must have a regular enough curl div in order for this formulation to make sense. Okay, with this in mind, what do we do about finite elements? So just taking inspiration without going into too much technicalities, taking inspiration from the de Rham complex again, we know that if we want curl-conforming elements, we need to have tangential continuity. If we want div-conforming elements, we need to have normal continuity. So we can make a guess, an educated guess would be, if you want to make the curl-div operator on a matrix make sense, that matrix must have normal tangential continuity, or sigma n. First multiply the matrix with a vector n, and the t is any tangential vector. The jump of this quantity should be 0 across. That turns out to be exactly the condition we need for the analysis to work out. So now the question is, how do you make elements like this? Can you can you make simple elements which have normal tangential continuity? Okay, so let's look at the lowest order case. And I want to convince you that there are simple elements just by looking at the normal vector fields on each of the facets. So here's a facet on the foreground, and you have a facet Fi, the normal of it is denoted by Ni. And just look at this matrix field, which is the outer product of the normal vector, the jth normal, with a cross product of two other normals on one face. And we're looking at this face. This is the face formed by JKL indices. Okay, so first observation is that if you have a constant matrix field like this, and if you multiply it with NK or NL, you get 0, because the cross product is orthogonal to its arguments. So therefore, we conclude that sigma n is 0 on the face opposite to AK, it's here, and the face opposite to AL. So it's 0 on two faces. Next, on this other face opposite to AJ, if you multiply this expression with NJ, you will find that the result is in the direction of NJ, because you just get a constant times NJ. So sigma NJ is in the same direction as NJ. Therefore, it has no tangential component. So we've just concluded that the normal tangential component of sigma n is 0 on three faces. So there are constant vector fields which have normal tangential component 0 on all faces except one. Okay, and now you take the deviatoric of this. The deviatoric turns out to not change the normal component. So this is now a traceless matrix field with 0 normal tangential component on three faces and non-zero on one. If you permute these indices, you still correspond to the same face, and you get one more function which has the same property. So we now have two functions per face that are piecewise constant matrix fields. And it turns out that that makes for 8 functions that span the space of all traceless matrices, of constant matrices. So this is the beginning of how to make finite elements. You can, of course, make it more complicated. Now you can go to higher order. Once you know that you can get these are the building blocks, and they are very, as you can see, very simple building blocks, then you can make higher order polynomials by replacing this by the gradient of the barycentric coordinates and putting further polynomials in higher order outside. Okay, this is how we make NT-continuous finite elements. You could also write it much more formally than how I've described the idea behind the construction. You can write it in the CLA style finite element definition. You have a geometry, a space. The space is simply the space of polynomials of degree k, or traceless matrices whose components are polynomials of degree utmost k. And it's a family of elements starting from k equal to 0 on up. And the degrees of freedom are simple. You take the NT component, the moments of the NT component are degrees of freedom, and interior moments with polynomials of degree 1 less are needed to make it unisolvent. And a pictorial illustration is this. As we've already seen, there's two basis functions in the lowest order case per phase, and these are indicated by these moments. These moments control these functions. Okay, so one last thing about this element, it comes with natural mappings. And the natural mapping is a mapping that preserves a normal tangential component. So in order to do so, we have to apply a covariant mapping from one side and a contravariant mapping from the other side. And that's exactly what's the form here. If you do so, then you have the property that the mapped element preserves the normal tangential component up to a constant factor on every facet. And it also preserves the traceless matrix property. So this means that the MCS method, all the variables in the MCS method, including the velocity variable, which can be handled by the standard PLO map for H2 velocity, the velocity, the pressure, the vorticity, which is like a TG space, pressure, which is like a TG space. All of them have come with natural mappings. So curvilinear elements are easily implemented. Okay, so this, I give you in detail one example of a matrix finite element. There are two other very interesting matrix elements on which I'll try to say very quickly. There are matrix elements with TT continuity and NN continuity. And just from the name, you can now guess what this means. This meant that you think of the matrix as a quadratic form, and then you feed in N and T, and you should have a continuous form, continuous function. Similarly here, you think of the matrix as a quadratic form and feed in tangential vectors, and you should get continuity across the element interfaces. And here, NN continuity, where feed in the normal vectors, and you should get continuity. The oldest is the HHJ element, the Hellan-Hermann-Johnson element, which is a symmetric matrix value, not unlike the previous one that we saw. The previous one was a trace-free matrix, and now it's a symmetric matrix. A symmetric matrix value finite element, which has a continuous NN component and simple degrees of freedom, or at least simple coupling degrees of freedom, just the moments of sigma NN. Now, originally the HHJ element was in 2D, and then now we understand the TD and NS is a 3D generalization of it, which has this sigma NN continuity. Here's another very interesting matrix value element, which has tangential continuity, or TT continuity. It's a space it's a 6-dimensional space controlled by these degrees of freedom, the moments on the edges of the tangential component of the matrix field. This is called the Regge element, and it has a natural operator. It's a double co operator, or a co followed by a transpose followed by a co. This is the operator known as the incompatibility operator in elasticity. It comes up when you linearize curvature, and there's a lot of interesting background for this element. Regge was a physicist who wrote an influential paper on relativity, and this element is named. Although you won't find any finite element in Regge's paper, this element is named after Giulio Regge. So this is another interesting matrix value element. And of course, this is the element that we have just seen. This is the traceless viscous stress element with NT continuity. So there are these three different types of matrix elements, and there are three different operators that appear to come. These are second-order operators that are natural for these. The co-div operator for this, the inc operator, the double col operator for the Regge element, and the div operator for the Hellan-Hermann-Johnson type of element. In the remainder of the talk, what I want to show you is a structure, a framework which allows us to understand these matrix fields together with the scalar and vector fields in some sort of an algebraically unified way. Okay, so there's going to be a lot of commutative diagrams in the remainder of the talk, and these commutative diagrams have vertices or arrows, or if you prefer to call them vertices or objects, or the arrows are morphisms. The objects, these dots here, they're going to be function spaces, and the arrows are going to be differential operators. I want to be able to specify the differential operators in different ways as we proceed. Okay, in this language, if you have a composition of morphism, this is called a path, meaning I compose these two, I get an operator, that's a path. This is a path. A path is called a complex if a composition of two successive morphisms vanish. For example, if this composed with this vanish, if this composed with this vanish, that's called a complex. And we've already been using the word complex before. We just didn't write the sequences in a zigzag manner, but rather in a straight manner. So this is the complex property. Successive operators should vanish. A 2 complex is a term that Peter Olber introduced in an old paper. And it's a generalization of this. Instead of 2, you say that you compose 3 operators, then you should get 0. So this path is a 2 complex if the composition of these 3 operators vanish, if the composition of these 3 operators vanish, and so on. Okay, and exactness, of course, is the range of one operator is equal to the kernel of the succeeding. And that's an important concept for complexes. For 2 complexes, we won't speak of exactness. Okay, now we go back to the classical Rham complex of mathematicians before finite elements and so forth. Let's look at a simple domain without any topological complications, a bounded contractible domain. The curly D is the space of infinitely differentiable functions with which are compactly supported on omega. So if you have the set of smooth functions and you apply the gradient, you get smooth vector fields. You apply the curl, you get smooth vector fields. You apply the divergence, you get smooth scalar fields. This is the Rham complex. And it is exact if the homology is trivial. From here, one usually goes, before doing finite elements, one usually goes into the Sobolev Rham complex, which is obtained by closing each of these smooth fields in an appropriate norm. If you close this in the H1 norm, you get H01. You close this in the H curl norm, you get this, and so on. And this is the Sobolev Rham complex. And these are the appropriate norms that we know. Okay, now from this as a starting point, we launch into matrix valued fields as follows. I have put the Rham complex here, and now I have vector fields, smooth vector fields here, smooth symmetric matrix valued fields here, smooth traceless matrix valued fields here, and followed by vector fields. Okay, now I'll connect these with these operators. The first is the operator that we called epsilon before, the symmetrized gradient. Okay, obviously a symmetrized gradient of a smooth vector field lands into a symmetric matrix field. If you take the curl of it, this is a simple computation. A curl of a symmetric matrix turns out to be trace-free. So you have a deformation operator applied, a curl of a symmetric vector field landing into the traceless matrix fields. Okay, now we're going to connect these 2 rows. I'm not saying that this is a complex. This was an exact sequence. I'm not saying that this is an exact sequence, but we're going to connect these as follows. With vertical operators that are also differential operators. This is the same as this operator. This is the same as the deformation operator. A strange looking operator appears here. The deviatoric of the gradient followed by a transpose. Now, okay, is it strange? Until you begin to see a property. If you put exactly that operator there, then this box commutes. Commutativity property here means that if you apply this and this, or you apply this and this, you get the same result. That is this identity. Curl of the deformation is the same as this operator, this operator after application of curl. Okay, this is just an identity that you can verify. There are more identities. So you can think of this whole diagram that I'm drawing as a way to organize a whole bunch of identities. This box also commutes. And this is when you begin to realize that this is exactly the operator that should go there. This is another identity. If you start from here and go here, get this. You start from here and go here, you get this. Okay, now I'm going to complete this into a bigger picture. I'm going to put this row as a column here, and you'll see a 2-dimensional picture where new things appear on this corner. Here's the complete picture. But again, we're restricting everything to smooth vector fields and smooth matrix fields. This row and this row is the same. they have the same information content. This thing in the center is something new, and this thing is something new. Okay, so the claim is that this is a commuting diagram, which means every box commutes. So you have more identities here. An example of an identity here is if you get the co-div operator by going this way, or 1/2 the co-div operator, that happens to be equal to the operator that you get by going the other way, from here through here. And the diagram is symmetric about the diagram. Okay, so this is the picture for smooth functions. Now we have a similar picture for Sobolev spaces. And you can see how the matrix valued Sobolev spaces fit in this central piece of the diagram. Okay, so before I can give you the Sobolev space picture, I need to introduce some notation for the Sobolev spaces. The dual of H01 is called H-1 in Sobolev space theory. The dual of H1 maybe it doesn't always have a commonly agreed upon notation. Treble's notation is H tilde -1. So here it has some weak boundary condition. So there is a little zero there. So we'll just call this H tilde -1. Using this H tilde -1, you can make a whole sequence of matrix valued fields. This may be a lot to look at, but the parts highlighted show you the key objects. The HCC has 2 cols in it. The HCD has a co-div operator in it, and the HDD has a double div operator. So these are matrix valued fields where one of these interesting second order operators play an important role. And and there are analogs of these spaces where you omit the tilde and you just put the H-1, the standard H-1, and you have these spaces. All these spaces and all these spaces, the only difference between these two are boundary conditions. Okay, so I'm going to give you this picture, this commuting diagram picture with these Sobolev spaces in a second. First, I'll start with the standard Sobolev Rham complex using H1, H-col, H2. There is a version with lower regularity. This will feature in the diagram. The version with the lower regularity, instead of starting with H1, you could start with L2 or L2 fields with 0 mean value. And then you apply the gradient. Then you end up with something in H-1 col where the Rabi-Thomas functions have to be taken off. And then you apply the col, you end up with something in H-1 div where the Nedelec functions are taken off. And the last one is H-1 functions where the P1 functions are all taken off. This taking out the Rabi-Thomas, you can understand it by looking at just what happens when you take the gradient of something with 0 mean value. Here's a function with 0 mean value. You take the gradient of it, you apply the distributional definition, move the gradient to the divergence. And if you're applying it to a Rabi-Thomas function, you find that this must be 0. So the gradient of it actually lands you into something where the Rabi-Thomas functions are not seen. Okay, so that's a bit of the notation. And here is a picture that looks very much like the diagram with smooth vector fields, except we've now supplied it with H1, H-col, H-div, or Sobolev spaces. And this is the low regularity sequence that I showed you before. The first row and the top row are exactly as in the previous slide. And the middle ones, this middle block contains the new Sobolev spaces, matrix fields. Now we prove a number of theorems about this. We show that this diagram commutes, it means every box in the diagram commutes, and every differential operator in it is a continuous operator in the indicated norms. And moreover, every differential operator has close range. This is important for getting into condition type estimates. And all paths in this diagram are 2 complexes. Okay, so this is perhaps a new feature. We haven't really been seeing two complexes in the literature before this. Saying that there are that all paths are two complexes means that you draw any path through this, and if you have three successive operators, you get 0. So maybe it's surprising, but if you can apply gradient followed by the symmetric gradient and then the curl, you get 0. Or take another path, you apply sim curl and then you apply div and another div, you get 0. If you stop right there and not take the third one, you may not get 0. But there's also, you can see there's a whole bunch of identities in this picture. Okay, this also reveals some fundamental second order differential operators. So you can see, okay, divergence and the gradient together gives me grad div. Okay, maybe we know a lot about grad div. Curl def is a curl followed by the symmetric gradient. That's an interesting second order operator. This is the operator we have seen appear in the Stokes, the curl div operator. Okay. This is the operator, the incompatibility operator, which is a curl followed by this transpose of the curl. This diagonal operator is the incompatibility operator. The div operator we've seen before, and the Hessian, of course, we know. Okay, so these are important second order differential operators because there are complexes using them that have appeared in previous contexts in previous literature. So here's the first complex. From this two complex structure, this rectangular commuting diagram, if you start with the Hessian and go this way, you get something called the Hessian complex or a low regularity version of the Hessian complex. The Hessian complex has others have exploited it with smoother spaces for other purposes. There's another complex hidden here, which is the elasticity complex. You start from the sort of a non-standard place for elasticity complex, the H curl, apply symmetric gradient and the incompatibility operator, and then the div operator. This is where the stresses and so the stresses live, where you apply the div. This is the elasticity complex, and there's one more, the div complex at the bottom. Which you can prove that all of these are complexes, which in the current set of assumptions happen to be exact. Okay, to understand these spaces a little bit more, we can do regular decomposition, which have been a powerful tool for not just understanding Sobolev spaces, but also to create some of the leading preconditioning strategies that came out of Livermore, for example. Right. So what are these regular decomposition? I'll explain that in the context of the standard Rham complex with some pictures, because things are getting really technical, and hopefully the pictures might help. So there's a gradient colon div, and you can have operators that go the other way. These are Bogovsky-like operators or right inverses of divergence, colon, grad. Knowing that these operators land you into more regular subspaces, this is indicated in the green color, we think of these spaces as compartmentalized into a rough part and a smoother part. Okay, and so this is like, we say that sometimes the Helmholtz-Hodge decomposition of H-curl is a space of gradients. This is the rough part, and the remaining part is a nice part. Okay. And how do we get this? What we typically do is, for example, for H-curl, we apply the curl operator, and the curl operator, once we apply the curl operator to the bad part is not seen by the curl operator. So going there and then coming back through the right inverse gets me something in the green box. That's how we construct these stable decompositions or regular decompositions. Okay, so I'm going to fill this with the rectangular diagram in a second. Again, how do we get decomposition of H-call. I just mentioned this, or H-diff, for example. This is the rough part. The rough part is in the form of a potential or a curl of something, and this is the regular part. So in order to get the regular part, you take a function here, apply the divergence. This part is not seen, and then come back via the right inverse, the TD. We can do the same process for all these new matrix fields. It just gets a little bit more complicated. Okay, so previously we just had the good guys and the bad guys, and now we have another gradation of badness. Okay, so this space is supposed to be the HCC space of matrix fields. It is decomposed into the green part, which is the H1 regular functions, the L2 regular functions, and there's another component where you can only expect H minus 1. And the way to get decomposition is you apply the inc operator. The inc operator doesn't see the bad parts, and then you come back via a right inverse that we construct, and that gives you this green part. And the other two parts are coming from a second order operator applied to an H1-like function. That the Hessian operator gives me this red part, and the def operator gives me this sort of orange part. So the regular decomposition now has 3 components of varying gradations of smoothness, and you go to the curl div space or the HCD space. That seems to be different from this because it seems to have 4 distinct components, 2 of them of the same smoothness gradation. You can decompose anything in the space in the form of a nice function and potentials coming from different areas of the diagram. And similarly, the H-div case is more similar to the HCC case. You have these 3 decompositions. Okay, so these are the decompositions we have, and we also had a similar looking diagram for the case without boundary. So the tildes are absent now. You're starting with H1. There's no 0 on top. This diagram also commutes. There are 2 complexes. The paths are 2 complexes, and all the previous properties hold. And I'm mentioning this because there's a very interesting connection between the 2 diagrams, the one with the boundary condition and the one without the boundary condition. And that's this picture. Okay. They are in duality. This is something we know. H01 is in duality with H minus 1. H0 curl is in duality with H minus 1 div. And the dual of H0 div is this. And there's a whole bunch of identities in this diagram also for the matrix value fields. So the dual of this, the dual of the curl matrix fields is the div matrix field, and so on. I don't know if it's pleasant to look at this diagram, it is too complex, or it's better to look at just a sequence of identities. So I've also written down a sequence of identities, which are also illustrated. You know the dual of H-div, the dual of H-curl, you know all of these duality characterizations. And we're working on trying to get a finite element and analog of this, and what structures need to be preserved is a open frontier. So I'm going to put up a conclusion here. We've seen a lot of things, hopefully not too many, and I have not overwhelmed you. But I started with a simple concrete example of the viscous stresses for Stokes law, and the MCS method seems to be a nice structure preserving method where a NT continuous matrix field naturally arose. And then I've described the ongoing attempts at making unifying structure of matrix fields with all of these older elements and these new elements. So thank you.
I've got a question. So when you have these decompositions of the different spaces in your complex, are those orthogonal with some inner product? For those orthogonal decompositions, I mean?
No, they are not. They are not like Helmholtz-Hart decompositions. They're more like the regular decompositions, which don't have the orthogonality of the Helmholtz-Hart decomposition. So this component need not be orthogonal to these.
Do you have estimates?
Yeah, they are stable, right? Yeah. So each of these components, these operators are continuous operators. So even though they're not orthogonal, we can bound this operator by the norm and sigma.
Yeah, it's a question.
It disappeared. Sorry.
Yeah.
It says, do you have the bounded cochain projections necessary for FEEC?
Yeah, we don't have bounded cochain projections yet.
So you don't have all the spaces.
Right. We don't. Yeah, it's an interesting question whether the matrix finite elements, the way that I had presented them in the lowest order case, whether we can directly put them in to the structure and get for example, exactness, and it doesn't. The dimension counts don't work out, so you have to add more stuff. So the story is more complicated.
So let me just ask something. So one very naive, I haven't looked at any of this stuff, but one very naive attempt will be to take the outer product of, say, Nedelec and Rabiatma, and that will have the anti-continuity. That's not enough?
I feel like that is more in the spirit of why not use Lagrange elements as 3 components and get a vector field that's normal. Okay, maybe it's a little bit more sophisticated, but
You're getting the dot products from left and right. So if you take vectors and have a rank 1 product with both of them are continuous, maybe it's too much. It's probably too much.
The dimension counts, I'm not sure are going to work out. So
I was going to ask, this is all for synthesis.
Yeah.
How do things look for tensor product elements? Have you looked at that?
For the MCS, there are tensor product elements. For the other ones, I don't know.
Usually things are simpler in that case.
That's a good point. Yeah.
And might be a natural way to.
Yeah.
So in practice, you have this in.
I think maybe I'm sorry. Maybe the prismatic Regge elements might be in Michael Neuenteuffel's thesis. I'm not sure. I have to check. Sorry.
I was going to ask, in practice, do you compute this, in ngSolve or?
Yes, these elements are all implemented in ngSolve, and we're using it in individual applications, like the for the viscous stresses. For MCS, we're using this for approximating curvature of manifolds. We're using the Regge elements. For elasticity documents, we're using the TDNNS. So each of these elements have found applications independently, and we just feels like there ought to be a unified structure.
And like for preconditioning those. Like following those decompositions, did you
open here?
You need to find the element spaces first.
Yes, of course. That's why that was my first question. Right?
Why stop at rank 2 tensors?
Okay. Okay. So the space of matrices can be decomposed in 2 ways. One, into symmetric matrices and skew-symmetric matrices. The other way is this hydrostatic the trace-free matrices and the remainder. You go to high-order tensors. There are other natural ways of decomposing high-order tensors, where this particular way of decomposing the rank 2 matrices comes out as one particular case. But to express that, we have to go into representation theory. So things are getting a little
nice.
technical.
There is one more question online. Is there any benefit to a matrix valued stress versus 3 vector valued elements, one for each row, as in AFW element?
As in AFW elements. Okay. So AFW stress elements with weak symmetry.
Well, went through elements with weak symmetry.
Yeah. So okay. So removing symmetry makes it possible to use 3 copies of vector valued elements, and then you have to reimpose the symmetry back as an equation of the method. That's certainly a nice way to get practical methods. But then you can also ask, why not impose symmetry inside the matrix field, and that gives you more complicated elements. In the context of this talk, the elasticity case is right here, which is the case where the div operator and an NN continuous exactly symmetric stress tensors live. That's so these are very surprising. It's just like when I started with the Stokes application, there were 2 different ways to go in Stokes. You could either set the h-div velocity in h1, or you could set the h-div velocity in h-div, and the different approaches seems to have different structures, and it's interesting to explore.
Let me ask you that daring question. This is very complex. So how about just using those Lagrange elements, just discontinuous elements, where you pay the price by that you have to stabilize it somehow? But how bad is it? Have you compared it on some problems?
I think it will be the same badness that you would see for let's say for Maxwell. Why not use, instead of network elements, why not use 3 copies of Lagrange elements? So the issues are usually well, there are some subtle issues where you don't even get the right solution because you live in a space where you converge to H2 intersection H co where you miss a singularity. You could have subtle issues like that, or you could have like other practical issues like locking, where you don't have enough gradient fields when you use the Lagrange element. But also from the point of view of preconditioning, it's important to know the potential space. Like if you're sitting here, you know from where the elements in the space are coming from. If they're coming from here, part of it is coming from there, and the rest is. So that structural information is important to construct solvers. These are the type of things that are missing if instead of the net elements here, you just put 3 copies of the Lagrange space. And I think my first guess is that if not knowing this structure would lead us to same type of mistakes for these more complicated spaces.